Yeah, these guys can be the same color, yes? So if I'm trying to minimize the number of colors, I want to identify the areas that can be the same color.
So if they touch, it can't be the same.
If they share a border, they can't be the same color. Okay, I like it. So you guys with me? Those two could be the same color. So if you want to kind of trace that on your paper, and then you pick a color, make them both green, yes? So let's say this is green. Come here, you. Say this is green and this is green. Yay! Now what's true about this one? Can't be green. So pick a color. Red, holy shit. And what's true about this one?
Can't be green or red.
Can't be green or red. So do you start to see, when you get a problem like this, you have to think, you don't have to think directly like this. What is the logic? But do you see how the first thing I noticed, I try to find my regions that can be the same color? Why does that logic make sense? If I'm trying to minimize the number of colors, I'm going to start with what's allowed to be the same color. Does that make? So everybody get the idea of this little game, right? This is an actual full-on, crazy-ass mathematical problem. And this is like a little example. Okay, let me stop for a minute. Does anyone who's willing to say so not get the point of this? You guys see the idea of this? I'm not saying can you mean to do it. You at least see the rules. So again, if all I needed to do was have each region a different, no two regions next to each other can be the same color, I could make them all different colors. But then they threw in the smallest number, yes? If I want to make the smallest number of colors, then some of them have to be the same color, so I minimize the number of colors I need. So then I can start with who's allowed to be the same color. That's a good starting point. And then you kind of work out from that. Just like we did with parties. So I'm going to let you guys do, Notice this region borders all of these regions. So whatever this region's color is, none of these can be that color, yes? In this, I don't want to do too much, but at least tell me this. Which two regions can have the same color? Any? 2 and 5 can have the same color. Anybody else? Oh yeah, look, this is a perfect example. 3 and 5, do they share a border? No, they only share a point. So either you can give 2 and 5 the same color or 3 and 5 the same color. Why can't you give all 3 of them the same color? Because 2 and 3 share a border, yes? Do you start to see how to break this down? Okay. I like it. Okay, that's a good question because that's a little tricky with the rules and what your end goal is. Yes? Okay. Anything else from homework? Because that one, there's certain problems in the homework that if nobody asks me, I'm like, nobody's doing homework because there's some problems in there that are just a little weird, as always. I'm sure they happened to you last semester or whenever you took it. Anything else from homework? No. So let me say this. Maybe this will spur some things. Let's have a quiz on Monday. Covering 12.1 through 12.3. If I remember correctly, what's happening a week from Monday? Test. So let me put some more stuff up here. Okay. Because some of you guys are not happy. I've left so much room for myself. So the test is Monday, what is that going to be? 10th? March 10th? Is that right? Huh?
This Monday?
No. When's the test? The 10th, there we go. The test is on Monday, March 10th. Which means on Wednesday, next Wednesday, March, you can do it, Jeff, 3rd, 4th, 5th. On Wednesday, March 5th, will be review day for the test. We won't do anything new on Wednesday, March 5th. Review? Yeah, Jeff. Review day for the test. I'm going to continue my list over here. On next Monday, we'll have the quiz, and of course, I'm going to give out a practice test. You don't have to turn that in. You don't even have to do it. You can get it from me. You can make it into a paper airplane. You can throw it in the trash, whatever you need to do. But that's just a study guide for the test. And on that Wednesday, I'm going to have the answer key for the practice test. Now, let me do this for anyone watching by video and for future Jeff. Future Jeff, hey man, this is what you said. Okay. Because if nobody watches my videos, I don't care because they help me out. I care a little bit. I'm like, man, nobody gives a shit. But I go, trust me. I'm going to go back and I'm going to watch this. I'm going to say, oh, hey, Pastor Jeff. Just so I remember what the hell I said. Okay. So any questions about how that works? This is our first real test. Yes? It's going to be on 12:1 through 12:5. So my plan is we're going to do 12 for today. Monday we'll have the quiz. We'll do 12:5 on Monday. And then, of course, Wednesday is review day. And I'll have the answer key for the practice test that you'll get next month. Any questions on all that?
So the test is 10.1 to 12.
No. Test is 12:1 through 12:5.
Oh.
Remember that chapter 10, 11, they lived on their own double quiz, they called it? Yeah. It will come back on the final.
Yeah, but those homeworks aren't due.
Yeah, I made those homeworks just to make it consistent. The homework is always due the day of the test. Yeah. I like it. Someday I'll actually grade the homework you give me. And someday you'll actually live my experience of, holy shit, I have no time. So this weekend I'm hoping to catch up on some stuff. We'll see. Okay. So nothing else from homework then? Okay. So I think last time we pretty much finished up 12:3. Just to kind of remind you guys, 12:3 is where we got into relationships. We created this little thing, we kind of expanded it. I don't know if you can get the expanded form. Oh yeah, there you go. There's the expanded form. So if you want to see this thing that we created, but actually be able to read it, you can do this. There's some folding exercises in here. Okay. So today we're going to get into 12:4. I'm going to lecture a bit, and then I'm going to give you guys a little worksheet to work on. I didn't have time to put my little animals in there, I'm sorry, so we'll just group us up somehow. Today you're going to work with scissors, which is great. So I've got enough scissors so that each group can have at least one pair of scissors. There's the awesome little tiny scissors that your finger can't quite get into. Hey! So 12:4 is going to be very exciting. It's a lot of geometrical relationships and definitions. So really, What are the main points of section 12.4? We don't, so real quick. What's the name of the theory that describes the levels of geometrical ability of students? I'll accept a few different ways to say it. Do you guys remember the name of the dude? Van Healy. I've heard it Van Healy, I've heard it Van Hilly, I've heard it a lot of different ways. Okay. So Van Healy, he's got level 0, level 1, level 2. So he made it up to level 2. 12.4 is now going to talk about those levels in a more formulaic way. We're going to today's going to be a lot of stuff that hopefully sounds very familiar. Do you guys remember the word transversal, for example? How about this? How about alternating interior angles? Does that strike any chord in your brain? Well, some of you guys are like, no. Okay. So 12.4, we're going to do some formalizing of ideas from 12.1 through 12.3. I kind of not warned you, but told you we were going to do this. 12.1 through 12.3 is exploring, is drawing, it's folding. Now we're going to get to the real mathematical part of geometry, which is normally what people don't want to do, but we'll see. So let me ask you this. If I have a line, how many points does that line go through? What's the idea of a line? How many points does it go through? Infinitely many. I love it. And what we normally do, the naming convention for a line, is I pick a couple of those points. So let's see, and I call them, normally we start with A, B, and I have a different line, I just keep going, C, D, blah, blah, blah. The actual, so that's the actual line. And the little arrows just say keep going forever. And that's what I'm approximating as a straight line. I don't think I've ever drawn an actually straight line, but we'll be okay. Does anyone know how to identify that line in notation? You guys remember, there's something about putting a symbol over AB. Yeah, you actually just make a little line. So you say this is line 80. So then if I have multiple lines, I can refer to each of them very quickly. Yes? Okay, I like it. What about, let me see, I might be getting a little ahead of myself, but that's okay. What kind of a creature is this? I like it. It's an array, and you're never going to believe the notation we use.
An arrow.
That's insane. Now it doesn't matter which letter comes first. Do you guys see that? So how would ray DC differ?
DC is a line symbol. Or is it
So this is ray CD. What would ray DC look like?
another arrow on
What would be the initial point?
there?
D, and then it would point in the direction of C. Okay. I like it. Okay. Does this kind of look familiar? You guys remember this? If not, does it make sense? So I can distinguish between a line and an array. And I think somebody just said line segment. Rays, of course, are important because they're different from lines, because lines go in forever in both directions, rays only go forever in one direction. What about a line segment? Just to cut to the chase, that's a line segment. stuck in. What do you call when I have a line and I have 3 points on the line? What would you say the relationship between those 3 points? There's one word I can use. So if it's called, they all live on the same line. So have you ever heard the expression cohabitate? If you have a roommate, you guys cohabitate. So this is called collinear. All three of those live on the line. So C, E, and B points, C, E, and B are collinear. What if I have three lines? Let's say this is A, B, C, D, E, W, just to be different. So I have three lines there. I got A, B, I got C, D, and I got E, W. They all connect at a single point, yes? So what do you think how do these three lines relate? This is a little bit weirder. This one we call concurrent lines. If you say something happened concurrently, you said that means it happened at the same time. So they all meet at the same location. So they're concurrent. So anything that doesn't meet, so if I have three lines that do this, this is remarkably not, we say these are non-concurrent lines. Okay, so again, today's going to be a lot of definitions. Hopefully some of it is kind of familiar. It might be a while since you've done this stuff. I'm never as worried about terms as I am about ability to do things, but in this case you have to know these because we're going to use these words and you have to know them so you can answer the question. What's true? What's the main point about two parallel lines? Pretend like these are parallel. So last time we did a folding exercise to kind of check if two lines are parallel. Well, what's kind of like the definition of two parallel lines? They never meet. They never meet. Now, really quick, just because we all live in, not a yellow submarine, but in 3 dimensions, yes? As far as we know, we'll just say that. 3 observable dimensions. So can everybody put their hands are lines. Can you all make parallel lines with your arms, I should say, not just hands. Can you all make parallel lines with your arms? Like this, yes? Now they never meet, correct? You with me? These never meet. Don't these also not meet? Are these parallel though? Okay, I just want to make sure I want to give you something you've never heard of, potentially. If I allow more than just living on a page, if I'm talking about 2 dimensions, saying they're 2 lines that never meet is all you need to say. Are you guys with me? This is kind of cool. These also never meet, but there's no way in hell you would say that this and this are parallel, correct? Okay. These are called skew lines. So lines in 3 dimensions that never meet but aren't parallel, they're called skew lines. Now help me out. If I'm on a page and I say 2 lines that never meet, that's all I got to say for parallel. Is that cool? What is another aspect of 2 parallel lines that would actually tell me this is not parallel? Because we all know this ain't parallel. Yes? They never meet, but they're not parallel. What's another thing about 2 parallel lines? What's true about, as I move down one line and the other one, what's true about the 2 lines? They're always the same distance apart. So these 2 are always the same distance apart, yes? These two, isn't this point further away from the line than this point is? So that's why if I make a more broader definition to include a few things, two lines that never meet, but always maintain the same distance, then that goes to any dimension I could be in. Okay. And if you ever have trouble with the word parallel has parallel lines in it. LL. So if I have line BD and I have line CM, incredibly creative minds of math people, what do I put between them to indicate that they're parallel? Just two little parallel lines. It's crazy. So I would read this as line BD is parallel to line CM. Okay. Now, a real quick thing. Do you see how the way I've drawn it, these are the same distance as, well, not quite. Make this bigger. These are the same distance as those, yes? So when we say they're the same distance apart, I mean in this case, a perpendicular fashion, yes? Because these 2 points are not the same distance apart as these two. Okay. All right. So not too bad. So, like I said earlier, this is something we all know. How many points do I need to create a line? 2. That's all I need. I don't care what dimension, man. I just need 2 points and there's a line between them. If I had 1 point, how many lines go through that? If I had just 1 point, how many lines go through that? So everybody make a point in the air. Now, isn't this line go through it? Doesn't this line go through it? Doesn't that line go through it? Doesn't this line go through it? Holy shit, so there's an infinity of lines that go through that. But the minute I give one more point, there's only one line that goes through both. I like it. And we all know this. If I'm given 3 lines, one of them might not be collinear, which leads to a problem. If I do, yeah, this is interesting. If I have 2 points on a line, I could talk about the distance between these 2 points. Now, real quick, if my line is diagonal, that kind of sucks. If my line was kind of flat, like this, and everything kind of lined up, this is 2, 3, 4, this is A, this is B. What's the distance between A and B? Two. I love it. But the minute I have a line that's diagonal, that's really sucks. Yes? Okay, so that's going to come back in a bit. So I can talk about the distance between 2 points, but it depends on the orientation of the line relative to the coordinate system I'm using. Is that cool? I mean, it's not, if I have a horizontal line that lines up with the x-axis, that's easy to see how distant 2 points are. If I have a vertical line, same thing. If I have a diagonal line to my coordinate system, that's where you have to bring in old Greek dude. Maybe. Blah, blah, blah. Okay. Oh, good. Already did that. Kick ass. Now here's something that's going to come back later this semester. How can I construct a line? Well, Later, we're going to talk about how to construct a line parallel to a given line. So if I'm given a line, and I'm given a point not on the line, this is a silly question. And everything we're talking about, by the way, for the most part, unless I have an aside, is in 2 dimensions, yes? It's a silly question. How many parallel lines go through P? How many lines parallel to M go through P? 1, exactly 1, exactly. Later this semester, we're going to have a line, we're going to be given a point not on the line, and we're going to construct the parallel. Now, if you try to draw it, especially me, I am most likely wrong. Because if I eyeball it, I'm probably off by like a little bit, you with me? But we can use compasses, and we can use rulers, and we can, not rulers, it's cheating a little bit, but we can construct a line that's parallel to line M. Okay. Oh, that's true. Yeah, okay, I'll come back to that in a bit. Let's see. Where? Yeah. Oh, good. Oh, yeah, let's do that. Okay. Sorry. I'm editing my notes as I go. Let's talk about angles. Can you guys just draw an angle for me on your paper? Just draw an angle. I'm pretty sure I know what most of you guys are going to draw, but let's see. Just draw a little angle, just living on your paper. He didn't exist before, now he exists. Like, I'm sorry. Did most of you guys, did anybody draw something different than basically this? Yes? Do it again, sorry. Oh, okay, got you. I love it. Okay, so what kind of angle is this? What's the name of this kind of angle? Oh, it's a cute little angle. Acute means an angle that is less than 90 degrees, between 0 and 90. And of course, what's a 90-degree angle? Right? And so you're back there telling me, oh, that's a nice, Jeff, your cute little angle, but I made, what's this do? Obtuse. Now, real quick, did anybody add anything onto your picture, or did everybody's look like one of those 3? So let me ask you this. Let me redraw my little cute angle. Yay. If I made this longer, does my angle change? Of course not. The mouth is still open the same, my beak is just getting bigger, yes? So I could put like that, and it would still represent the same angle, yes? Both sides of the angle are what kind of things? Both sides of the angle I've just drawn are what kind of geometric shapes?
Or rays.
Rays, exactly. So if I give myself, both of them share a point. So I've got ray BA, I've got ray BD. And again, I gotta be careful about the B coming first because that's the origin point for that. Is that one of our, I can't remember. No. What's another name for this point right there? It's the what of the angle. I don't know if you guys know this. Like if I draw a parabola, which is basically an angle that has curved sides, what's this point? You guys remember? Here were letters that look like. V. Starts with V. Vertex. I love it. So this is called the vertex of the angle. Can somebody give me a name for that angle?
ABV.
Yeah. Did I talk about this a little bit already? I can't remember.
It was part of what the worksheet was on.
Oh, good. Okay. What else could I call this angle? Good. And I could also call it DBA. You could do it, Jeff. Okay, yeah, I remember this. We talked a little bit about this already, where I can't do this in every situation. If I had another angle coming off of there, I couldn't do it. Okay. I like it. Yeah, I did get a little ahead before. That's true. Here's something kind of nifty. We normally consider this to be the interior, and this to be, remarkably enough, the exterior of the angle. Now, this might seem a little strange, but like your protractor, what's the highest degree it goes up to? 180 degrees, yes? So we don't have this, these exist actually, but we don't have a perfectly round protractor, and that's because if I had an angle that did this, I would just turn my protractor around, or turn the paper around, yes? So, you could have a 237 degree angle, but then we would consider, that would be like this, yes? But then we would consider this to be the interior of the angle. Now this leads to a very strange kind of side note in geometry. Yeah, perfect. So let me draw this again on the next page. If I pick any 2 points on the interior, pick any 2 points in the interior, if you connect them with a line segment, is it possible that that line segment goes outside into the exterior? Do you guys see that? So if you pick any 2 points, any, and you connect them with a line segment, is it possible that line segment can go outside of the interior? If you say yes, I want you to show me. So if I pick any 2 points that are interior to the angle, it is impossible for the line segment between them to go outside of the angle, to go to the exterior. Is that okay? Kind of a strange little side note. On some level it should be like, of course you can't, Jeff. What are you talking about? So we would call that kind of area where any 2 points in the area only connect within the area, we call that convex. Has anybody ever heard that word in a different context? Yes?
Like convex and concave.
True, yes, in fact, and remarkably enough, the other side's going to be concave in a minute. But no, you're fine, don't worry. Convex and concave what's? Okay, good. Have you guys ever looked at yourself in a spoon? Have you ever stuck a spoon on the end of your nose? What the hell are you living? Okay, so if you breathe into a spoon, you can hang it on your nose, yes? Some people, of course, have a nose and they can just hang on it no matter what. Have you looked at yourself in both sides of the spoon? Have you looked at your side view mirror? Or some of you guys go, I have a mirror? Shit. Some people on the road, I'm like, I think they know they have a mirror. And it says objects are closer than they appear, which on one level is like, well, that's just me. I thought I had room and I didn't. And that's because of the curvature of the mirror. Now, why would they curve it? Why would they curve it, the mirror? What do you want to be able to see from in the car? Do you want to see more or you want to see less? More. So if I curve the mirror, I'm going to be able to see more. But the trade-off is they're going to look like they're a little further away than they really are. So if you look at yourself in a spoon, both sides of the spoon, you're going to look closer and further away based on whether it's convex or concave. Okay, let me stop for a minute. How about lenses? Have you guys ever heard of convex lenses, concave lenses? I might have to, I might want to do this at some point. You could do some cool ass shit with lenses and light rays and so forth. I might have to do that at some point. Okay. So this, in fact, this is a very general idea about any region anywhere. If any 2 points connect and the line segment does not leave that region, it's convex. And do you guys remember the idea of closure? You guys remember like whole numbers are closed under addition? That idea, do you guys remember this? You guys remember what that meant? If I take any 2 elements and I add them, the answer must still be in the whole numbers, must still be in the set. This feels a little bit like if I take any 2 elements in the region and I connect them, it's still in the region, it doesn't leave. What about if I take 2 points? Can you take 2 points in the exterior and connect them and it goes from exterior to interior? Can you take any 2 points on the exterior of the angle, connect them, and it doesn't stay on the exterior? Yes, you can. How about this point and this point? What happens if you connect those? They're both on the exterior of the angle, correct? What happens when you connect them? Oh shit, I didn't stay on the exterior. So if I have a region anywhere, it doesn't have to be angles, it could be any shaped region. If there's a possibility that any 2 points, when I connect them, so for example, this shape. Yes? That's the sound it makes. These 2 points are good. That's my guy with the unibrow. Leave him alone. These 2 points, oh shit. Yes? So I would call this concave. What about a circle? What would I call a circle? Is it concave or convex? Why? I can't imagine, there's no 2 points that I can pick that will go out and come back in. There's no 2 points that when I draw a line segment between them, that line segment leaves the circle. It will stay in. You guys get that idea? So of course the whole idea is convex and concave. That's convex and the other one, so this is convex. This is concave because it caves in, yes? Okay. So you see how the circle is like on the outside of it, it's always curved out. So that's concave because you come in, all right, I'm not gonna get too into that. Convex is if every line segment between any 2 points stays. Concave is if at least one line segment leaves the region and comes back. Okay. That I'm pretty sure you've never heard of, especially in terms of angles. Blah, 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 blah. Concave, convex. Blah, 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 blah. I'm pretty sure I did that already. That's interesting. Yeah, okay. Obviously, we can measure angles with a protractor. The neat thing about angles, let me see if you guys know this. If I measure an angle and it's not exactly 30 degrees, do you guys know the subdivisions of degrees? For example, if I measure somebody, they might not be exactly 6 foot. If they're a little off from 6 foot, what's the next measurement down that we use? I'd say they're 6 foot, 2 inches or something, right? So there's feet, and they can be broken down into 12 inches per foot, yes? I like it. So angles can be broken down a couple times. Does anybody, you guys know about this? So, and it's kind of nifty. How many minutes in an hour? And how many seconds in a minute? So if I have 1 degree, we actually just stole it. That would be 60 minutes. And 1 minute is 60 seconds. So I could say that this angle, oops, sorry. You guys ever seen that symbol before? I kind of drew it a little hastily. It's theta. Let me just call this angle A. I could say the measure of angle A, I could say maybe it's 30 degrees, 2 minutes, 5 seconds. I didn't mean for there to be that there. A little squiggly line is just a stray dot. 30 degrees, 2 minutes, 5 seconds. So it's a little more than 30 degrees. So if you've ever been out on a boat, this is how you identify where you are if you want to be more precise than just a number for latitude and a number for longitude. Yes, longitude. Just like saying he's not 5 foot tall, he's 5 foot 2 inches. Yes, you're a little more precise. Okay. Blah 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 blah. Okay. So let me give. Does anybody? All right, this works best if we use blank paper. So we're gonna use this paper for a couple things. So do what we're about to do on one side, and don't do anything on the other side. Later we're gonna do something on the other side involving some scissors and such. So. Anytime. So. Okay. Anybody? Did anybody bring their kit? All right. There should be at least there's a protractor in most of them. Yes. All we really need right now is a straight edge, though. So let me know if you need a straight edge. Anybody need a straight edge? Is everybody good? Because at least the protractor has a straight side to it. You need one? You need one? Oh, sorry. That's useful. All right, guys. So for right now, what I want you to do is very simple. Is it Jeff? Let's see. I just want you to. Doesn't matter how big, how small. Maybe, let's see, maybe up here in the top, just draw a line. And then I don't care. Just anywhere else, draw another line that intersects that line. Yes? Doesn't have to look like that. Doesn't have to be that long. Doesn't have to anything. I just need a line and another line that intersects it. Okay. So everybody's drawn a slightly, look at that little tiny dude. Everybody's drawn a slightly different picture, I would say. Now, a lot of what we're going to do this semester, we're going to sort of temporarily forget we have a protractor. And then we're going to go, oh yeah, we have a protractor. So a lot of what we're going to do is investigations without a protractor to construct certain things. This one is just a quick illustration of whatever this angle is. And let's give these guys names. I'm going to call that one A, this one B, this one C, and this one I'm going to call D. That's crazy, Jeff. Let me make this a little different, darn it. You guys all with me? Can anyone tell me anything about the relationship between angle A and angle B?
They add up to 180 degrees
Why?
because it's
Because they make, now here's really an illustration of why people don't like math people. We call that a straight angle. It's like, sure, whatever, math people. But A and B together make a straight angle. Does anyone know what that means about angle A and angle B? There's a certain name for two angles that add up. So the measure of angle A plus the measure of angle B. Don't just say A plus B. That doesn't make any sense. The measure of angle A plus the measure of angle B is 180 degrees because together they make a straight line. Does anyone know the name that we give two angles that add up to 180 degrees? Supplementary. Hello. So two angles that add up to be 180 degrees. They don't have to actually be drawn. They can be drawn separately, but as long as they add up to 180, we call them supplementary. Supplementary angles. What about A and C? Is there a relationship between angle A and angle C? That's trying to be a little n, but it didn't quite make it. Is there a relationship between angle A and angle, for everybody? All of us have the same relationship. What do you guys think? They have to be the same in measure, yes? Their measure has to be the same. Continue to me, why? No, complementary will be if they add up to be 90. So just because you said that, I always remember this alphabetical order. Complementary is 90, supplementary is the next letter, so that's 180. It goes in order. Complementary, supplementary. So A and C are equal, basically because they were constructed in the exact same way. Does that make sense? They were constructed the exact same way. They exist for the exact same reason. Do you guys know what we call those kind of angles? And again, what letter does this look like? V. So these are vertical angles. Yeah. Okay. So those are two angles that are equal in measure because they are vertical angles. So whenever you have vertical angles, they will be equal in measure. So anytime you have one line intersecting another line, the angles across, so of course B and D are also the same measure, they are also vertical angles. In general, if I have two angles, equal in measure, equal in measure, we call them congruent. And of course, we've seen the word congruent before, I'm pretty sure. Congruent angles. So two vertical angles are congruent, meaning they have the same measure. Okay. Blah, 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 blah. Oh, did I forget something? No. Good. Blah, blah, blah. Blah, blah, blah. Blah, blah, blah. Oh, we already talked about that. Okay. Now we get to some neat stuff. Okay. On your paper, let's see. Now we're going to do this freehand. Later this semester we'll be constructing things. Let me see if you guys can do this. I want you to, as best you can, in the little, on the down, lower part, same side, because the other side we're going to do some other stuff. Draw a line, and then try to draw a line parallel to that line. So we're doing this right now by sight, so it's not going to be perfect, but it's going to be close. So that on sight looks pretty parallel. I would bet it's not perfectly parallel, but it's okay. So everybody got their two little parallel lines. Okay. Let's call them L and M. Now draw, I don't care what angle it hits, but draw another line that goes across both of those. We'll call this line T. How many angles did I just construct? 8, yeah. Now, of course, you could think about 2 again, but we have 8 kind of component angles we created, yes? Wouldn't you agree with me that the 4 angles that T and L make were constructed in the exact same way the 4 angles that T and M make? So this is a lot like the vertical angle argument. What should be true then? Well, first off, so let's number these. Angle 1, 2, 3, 4, 5, 6, 7, 8. Let me make it so tiny, Jeff. What must be true, for example, about angle 2 and 4? They have to be, they're the same. Because they are vertical angles. Now, what must be true about angle 2 and angle 6? Oh shit, I'm sorry guys. Always remind me when I have stuff in the way. Grr. What do you guys think? Angle 2 and angle 6? Not just because it looks so, but because the way angle 2 is constructed is the exact same way angle 6 is constructed. So I could just, since these are parallel, I could pick up line L and put it there on line M so all of its angles kind of match up. These 2 angles, angle 2 and angle 6, we call them corresponding angles, which makes sense because aren't 2 and 6 in the exact same relative location? 2 relative to L is in the same location as 6 relative to M. So we call those corresponding angles. Is there another set of corresponding angles? Give me one more set of corresponding angles. 1 and 5, 11. Somebody else give me another one. Good Lord, Jeff. 4 and 8. Okay, and you guys see the idea, yes? So every pair of corresponding angles are equal in measure because in some sense, they're the same angle. Just kind of like moved a little bit. Since those are parallel, would that work would any of this work if L and M weren't parallel? No. Only the vertical angles would be okay. So let me ask you this. Angle 4 is equal to angle 8, yes? How do you think, all right. Here's a little bit of geometrical math. The measure of angle 4 equals the measure of angle 8 because they're corresponding angles. What's true about the measure of angle 8 and the measure of angle 6? They're equal. So this is because they're corresponding. Why is this equal? Vertical. Jeff. So what do you think about the measure of angle 4 and the measure of angle 6? And this little property is called the duh property. Well, it's actually called the transitive property, but I call it the duh property. If you're as old as she is and you're as old as she is, then you're as old as she is, duh. So this says angle 4 is the same as angle 8. Angle 8 is the same as angle 6. So how do angle 4 and 6 relate? They're freaking equal. Of course they are. Because they both equal the same other thing. Yeah. You guys kind of with me? Now, do you see, all right, if 4 is the same as 8 and 8 is the same as 6, 4 must be the same as 6 in measure. Okay. We give this its own name though, and I said it earlier today. Wouldn't you agree with me that 4 and 6 are inside? And like 1 and 7 are outside, yes? For example, do you guys see what I mean? 4 and 7 are inside this train tracks. Like 2 and 7, for example, are outside. So we call 4 and 6 alternating interior angles. So like 3 and 5 are alternating interior angles. So whenever I have, where'd I go? Here. Whenever I have, and by the way, I labeled this T for a reason. And I said this word earlier today. Does anybody know what the name of this line is that comes in and runs over my two parallel lines? Do you know what the name of this guy's? Starts with a T. Transversal. Let me see if we get it. Yeah. Let me see. Whenever I have two parallel lines and I have a transversal come in, all of these relationships will hold. So what if I have two parallel lines and something like this happens? Automatically, every single angle I created must be 90 degrees, yes? Because you got vertical angles, then you got 90 plus 90 is 180, you got vertical angles, and then you got alternating interior, and there's alternating exterior, by the way. Angle 1 equals angle 7. Hopefully some of this sounds familiar. Blah, 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 blah. I want to make sure I didn't miss anybody. No, okay, good. Blah, 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 blah. Okay, let's do this. On the other side of your blank piece of paper. Actually, wait a minute, I'm sorry. I don't have enough scissors for this. So let's do this. We're gonna do the scissors thing in a bit. So this first set, and very quickly, I know I gave you this, and this is because this is an actual worksheet that somebody's used before, so I wanted to show you an example. Do you guys see an issue as a teacher you might have with this kind of problem from the student's perspective? Let me see if you guys are with me at all. Angle 6, couldn't I take a protractor and measure the damn thing? Now, I want you to understand, I'm talking on a meta level about a worksheet. Just about, there's nothing necessarily wrong with it, but there is one little thing that kind of irks me. Didn't they just say measure of angle 6 is 72 here, and then down here they said it's 13? Do you guys see what I'm saying? And again, I know I gave this to you, but this is one reason why I wanted to give this to you, because this is an actual worksheet out in the wild. So do you think a student could possibly get confused then? So you might, if you do something like this, you might want to have several things to reference. Do you see what I mean? Okay. But for the purposes of efficient use of space and all that, this kind of makes sense, but just be aware that could be very confusing. Because angle 6 has a measure. It does. I can put a protractor, I can see what the hell it is. And these stupid things are telling me it's two different things. Okay, so that's one thing I just want to throw out there.
So does that mean you're saying that, like for 24 says if, they would use that if as an answer key, so they would say angle 7, so then they would go back to 20 and then write.
They might label it and mess them up later, or they might get really confused why it's saying it's got two different measurements.
Okay.
My teacher said it's got to have one. You know what I mean?
Okay.
So this is just, if you create your own worksheet, or if you, what a lot of teachers do, because a lot of us don't have a lot of time, is we steal stuff from other people. We cobble it together. Just be really careful about potential confusing parts of something you give your students. And again, I know I give this to you. But that's one reason why I wanted to do it. It's not a bad problem, it just could lead to some confusing things. So, with all of that said, angle 6 and angle 7, how are they related?
They add up to 180.
Kick ass. So what kind of angles are they? So supplementary, okay. So what's the angle, what's the measure of angle 7? What'd you guys see? 108. 8 and 6 have to be the same because they are. Like somebody's doing the vertical. Okay, so this obviously 8. Bam. 9 and 8 have to add up to 180. So in this universe, where angle 9 is 110, angle 8 has to be 70. That's crazy sauce. 9 and 7 vertical. So in this universe where it's 123, this one has to be 123 because vertical angles are equal. So maybe you can think of this as a multiverse kind of situation. Angle 7 and angle 8, again, they have to add it to 180. Now, really quickly, I'm pretty sure you guys picked up on this. Isn't there like, you're like, I already did problem just like that. Did anybody feel like that as you're doing this? When you're first learning this, one thing that student might have trouble with is 6 and 7 want to make 180, but 7 and 8 are different. Why would they also make 180? So they have to reanalyze it from that new perspective. So that's why a lot of worksheets for younger kids have a lot of repetition, because you want to make sure that that relationship holds no matter where the stuff is. Yes? Okay, maybe. All right, so 7 and 8 have to add up to 180. So what'd you get for angle 8? 38 degrees. I love it. 6 and 9. Yeah, add up to 180, so you get 167. Kick ass. 9 and 6. Add to 180, so that's 10 degrees. And then 8 and 7. Add up to 180, so that makes 154. I like it. Okay, that was nice. Bodacious. And then we hit this. So, I kind of like big groups, but also just one person in a group is good because they really make sure you both get a chance to talk, for example, right? In a big group, some of us might feel like, what kind of situation am I in here? Yeah, because they're vertical angles, so whatever the hell they are, they must be equal. So you could at least write this down. And then some of us were like, oh shit, I don't remember. So here's the idea. Here's how I teach algebra. I'm trying to get my x. Somebody buried my x under a bunch of frickin' shit. Yes? I'm gonna go somewhere. So I want to unbury it. So what's funny is I kind of do order operations out of order. So I'm going to first add the 11. So what I try to tell my students is, where is my x in the term 2x? Yes? Why is that term not by itself, the stupid minus 11? How do I kill the minus 11? I plus 11, yes? So I'm kind of like unburying my variable as I go. So I'm going to take the first level away, add 11, and now the 2x is down there, it can hear me, I'm like, yes, I'm down here. And then the last level I have to get rid of is a 2, and of course what do I do with the 2? Divide by 2, because the operation is multiplication. And I end up with 58 degrees. And if you get that, you can check it. Twice 58 is 116, minus 11 is 105. Yay! This one's a little extreme, but if you rotate it, what do those two angles have to do? Add up to 180. So if I subtract 19, I get 161, yes. Divided by 7, what do I get? 23, kick ass, degrees. Yay. How are we doing? Is that okay? I'm going a little fast because we got a lot of these to do. You're all like, yeah, Jeff, you did that. 30, I'm in a situation where what? They equal each other, nice vertical angles. Check. So add 2, divide by 5. What do I end up getting? 16 degrees. Then again, you can go back in and check it. All right, how are we doing? Yes, sir.
Would x have to have the degree symbol, because it already has.
Oh, true, good point. I wouldn't need degrees on there, it's just a number. Being a little overzealous. Okay. What about, now we move on to parallel lines and transversals. And they started us off nice. The problem doesn't ask you this, but why is what you're about to tell me true? How do those interact? Those are, how are they the measures? They have to be, what's the relationship? They're corresponding, good, which means they have to be the same. So 70 equals 3x minus 14, add 14, divide by 3, and you get 28. Like Gabe said, I don't need the degree symbol because they already have it on there for me. Thank you, sir. This one, you can see how a student could miss this pretty easily, but that's a nice set of perpendicular lines here. But what's the situation here? These two aren't necessarily directly related, correct? But as I told one group, if you kind of label the other angles, what's true about angle 4 in this angle, for example? What's true about these two? Now this one's got a, I'm trying to set something up for later. This one's a little silly. Let me just say, hopefully everybody did it this way. I'm trying to help us out for later. This one's almost silly. The minute one of these is 90 degrees, what's true about all of them? They're 90 degrees. Did anybody do it that way? I know you guys did, so let's see. Or 4 and 90 have to make 180. These two are equal, therefore these two have to make 180. Yes? Since that's 90, this one just has to be 90. So this one just has to be 90. And you end up getting minus 10 divided by 2, 40. Is that cool? How are we doing? Okay. Do these two relate directly? No. What about these two? What's true about those two? You could also say this is alternating exterior, but what's true about these two angles here? This angle and this angle have to be the same. I'm sorry, I think it says, somebody said that, I didn't hear. And of course these two angles have to be, so therefore these two angles have to be the same. So you can either do alternating exterior angles, or you can kind of work your way that way. Whoops. So I get 12. Is that cool? Add 9, divide by 12. Okay. And you know, the rest of these basically work the same way. So I was trying to tell one group if they label all the other angles, this and this are the same, yes? These two are the same. And these two have to make 180, therefore these two have to make 180. Is that 89? Yes. So we get 5x plus 65. Subtract 65, I get 115, divide by 5, 23. Jim Carrey would freak out. Same idea here. If I kind of give myself labels for all of them, how can I say this? This one and this one, they have to be equal. These two have to make 180. Therefore, this one and this one have to make 180. Does that say 5? Plus. Does that say 5? Yes, I can't read it. Plus 94 equals 180, yes? 13x plus 89 equals 180. 13x equals 91. X is 7. Woo! And then this one's nice. What's true about this one? Yeah, so if I look like that, there's my transversal. These are corresponding. This is a little trippy because the first thing you have to do here, you don't have to, but I could distribute, yes. So let's say 126. Add 49, I get 175, divide by 7, 25? Let's see, did I do this right? Add 49, yes. Oh yeah, 25, yes, okay. Yay! Okay. These are based on the idea that all the angles in a triangle have to add up to be 180. So I love the fact that as I was walking around the room, somebody was using some algebra. You don't have to use algebra, right? Whatever these two add up to be, that one's got to make it equal 180, yes? So what do these two add up to be? 91 degrees, so this one's got to be 89 degrees. I like it. Same idea here. These two make 116. So then what's this guy got to be? Yeah, 64 degrees. Is that cool? Just trying to force him to add it to be 180. What about this one? Did they give me enough information for this one? Yeah. The stick in this mouth is the same size as the stick in this mouth. So what kind of triangle must this be? Well, it's eventually right, but immediately it's isosceles. So this one's got to be 45 degrees also. So this one's got to be 90 degrees. Pretend like that's at the box. Okay. And of course, same idea here, and same idea here. I'm not going to do this. I think we can all do this. Those are a little bit easier. You don't need any algebra for those. Is that okay? Just kind of cut to the chase a bit. The whole idea with all of these is what? They equal to 360. I'm going to prove that here in a minute. So I can do the exact same thing that we just did, 90 plus 100, because that's 90, plus 95. I can see where I am so far, and then I can see what I need to make 360 total, right? This will be 285. A little something from Math 125. What is this approach to the idea of subtraction? Missing add end, kick ass. So I want 285 degrees plus something to be 360. And of course, what is that? 75 degrees, kick ass. Same idea here, yes? Same idea here, yes? Okay. Is that okay? I'm going to skip those just for time. Then down here, I got some algebra again. But this one's kind of silly because this one especially is silly because I can just do it the same way we just did. So x plus all of these, what is that, 293?
Yeah.
And then you can just subtract to get what x is. So that would be 67? Yes. And again, let me let you reverse it once. This one is kind of silly on one level. That's 90, that's 60, that's 150. So whatever this angle is, it must equal the rest, yes? 60 plus 150 is 210 plus 90 is 300. So whatever this angle is, it must be what's left. So that's 300. So this one's got to be 60 degrees, yes? And then I just divide by 3 to solve for x. I don't need a reasonable number. there's same idea here. Well, it's got to be true if I add up all these degrees. $360, and then I get a little equation to solve. So I'll get 184 plus 4x equals 360. Subtract 184. 4x equals 176. Divided by 4. What is that? 44? Yes?
Yeah.
Okay. The trippiest one I think was probably 46, but I'm not sure if you guys all made it down to that point. Because this is the same idea, this is the same idea. This is the same idea, but now I have an x squared, which was a little evil. But, here's the idea. 90, 90, 99, yes? So what is that, 279? So how do I figure out what x, no, not equal x squared. So x squared would equal 360 minus 279. It's gotta be the rest, yes? So that would be 81. And of course x would be 9. I like it. In general, it would be plus or minus 9 algebraically, but you know, it's a freaking angle, so I don't want it to be negative necessarily, especially because it lives inside of an object. Okay, so last thing for today. You guys have been so patient through all the algebra business. Shoot, I should have made sure you stayed in your groups. It's okay. Somebody next to somebody. I think how many scissors do I have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So as long as you got somebody with you, I can give each group 1. So, let's do this part first. So everybody find one person there. I think all of you are still kind of grouped up. Yes, I love it.
Thank you so much.
Kick ass. Can everybody, on the other side of that paper we were using earlier, on the top half of the paper, it does not matter what kind of triangle you make a triangle. And here's what's really, really nice. We're going to cut these triangles out. So look what I can do. I can just, do you see how I can just do that? You guys see what I'm saying? So don't worry, because I'm going to cut this triangle out so I can just do this. So I make sure Jeff, good boy. I could just do this. So I make sure I make a triangle, yes? And then I'm going to cut it out. So it doesn't matter that I went past it. This is not a triangle yet, officially, but then I'm going to cut it out. Is everybody with me? Label your angles. Holy crap, what happened to you? Any way you want. I'm going to label mine ABW. Okay. Now, I'm going to give each group scissors. A designated cutter. Oh, shoot. So go ahead and cut your triangle out. Oh, shoot. Take turns with the scissors. Oh, I should have left one for myself. Oh no! Who would I give an extra one to? Yeah, they're you guys share that one. Well, these are really bad. Let me see if I can do this one. Wait, these are fine. User error. Ah. Okay. Now, obviously, us imperfect humans are doing this, so this is not going to quite perfectly work. So everybody got their little triangle? Now that this triangle exists, we're going to immediately cut them up. So let's see. Here's what I want. Everybody, watch. I'm going to draw this in first. I'm going to cut here, I'm going to cut here, and I'm going to cut here. Yes? So cut through to the center. So basically we're chopping the angles out. Yes? So I'm going to cut through to there. I'm going to cut through to there. And I'm going to cut through to there. So I've chopped my poor little triangle up.
Give me back the ruler.
Oh, thank you. Now, if you take your three angles and put them together, what do you get? Straight line, yes? So you got 180 degrees. Cool. So this is, now real quick, protractors are not difficult, but they are very difficult for very young people. Yes? Cutting is difficult too, but you know. So before we show them a protractor and how to read it, this is one way to kind of show them that all the angles in a triangle make 180. Yes. One last thing, and then we'll head out. Let's out nice and early. On the other half of your paper. Thank you. See you guys. What's up?
You said I'll read you guys out early. It's already 10:52.
Yeah, it's already like 10:55.
Oh, I'm sorry. Oh, what time do we go to?
10:50.
Oh, 10:50. Oh, shit.
That's what
I have my other class in my head. That's enough for today. I'm sorry. I did mean to let us out early, and I just mixed it up
I know
again.
we said I'll read you guys out early. I said you're already past.
I'm sorry.
Keep up here, another second.
I was gonna keep us here till 11.
Yeah, thank you.
Oh, these scissors in general.
It's just the type of scissors.
Oh yeah, like rulers too. Yeah.